It's my pleasure to welcome Paul Ginsparg, pictured here on the front of your program. Paul has a BA in physics from Harvard. He has a PhD from Cornell, where he's been a professor since 2001, and has held faculty positions in physics at Harvard and was a staff member in Los Alamos. Paul has made significant contributions to many areas of physics, conformal field theory, quantum field theory, string theory, just to name a few. He's the recipient of many deserved awards. He's a fellow of the American Physical Society. He's a MacArthur Award winner, a White House champion for change. One of Paul's biggest contributions was creating the archive, which is a website that has transformed many disciplines of science. It's a clearinghouse for publications, for preprints, and it's really revolutionized the way that academic publication works. And I believe archive was first created actually here in Aspen. On a personal note, Paul also wrote a very well-accepted pedagogical standard review of conformal field theory, which is used widely in the field and was influential in my own career in teaching me conformal field theory. So thanks.
Why did you never cite it?
I've already seen that slide. Anyway, so yeah, without much further ado, let's welcome Paul.
Thank you. It's good to have an introduction like that, because otherwise I'm feeling very intimidated talking about a subject on which I'm completely inexpert. As I said in the, here in, did I do that? Just that I'm, something of an outsider of the field. I'm at Cornell in the physics department, jointly in the info sci department. But it's a fun challenge, and I'll try to convey some of the basics. I'll start out, as Ethan mentioned, the archive, which is has become the standard way of communicating information in physics, and more recently, in this machine learning community, which is part of what got me into it. It really did have its origin here in Aspen. And so I'd just like to start out with a few slides. Does anyone recognize this? So this was yesterday afternoon. There's the little swing at the top, and then spectacularly virgin snow. Nobody was there before I got to it yesterday afternoon. And so I got to crawl all over the rocks. It looks fake, but this is what we love about this place. These little dots over here are skiers. And there are the gondolas. Okay, so the basis of this talk is we've all heard and been reading over the last 5 or 6 years. When I mean we, I mean seriously, because it's been all over the mass media. I'll have a bunch of screen grabs from the New York Times, just breathlessly trying to explain to us or reveal to us the latest and greatest advance in machine learning, whether it's being able to play video games or recognize speech. We've seen the apps that do that, translate languages, or, of course, self-driving cars. There are a variety of aspects of this. It's, beating humans at Go, beating them at chess, and a variety of aspects that involve superhuman performance. For example, in image recognition, these systems can now read a sign at 60 meters in the fog that a human would have no chance at. And so, this is the inevitable future. We'll be seeing, and superhuman performance is a technical term in this. Whenever you have a metric and the machine outperforms the human, we call it superhuman. And, I'm going to end on a positive note, which is that, like any other tool, we should take advantage of it. But my plan is to first give you a quick teaser of an application which is not looking at 1,000 images and distinguishing a dog from a cat, but something that's closer to heart, as it were, in image analysis, which is a wonderful example that I learned from in a colloquium from Jeff Dean, given it from Google, given at Cornell in the fall, where the backstory is for 100 years, these so-called retinal fundus images, this is just an image of the back of your eye taken through your pupil, has been used as a diagnostic tool. It becomes immediately obvious when you think about it. This is the only place you can non-invasively image, capillaries. Anywhere else, you have to cut in and you do all sorts of damage, but you just stick a bright light and a camera into somebody's eye, and suddenly you can see all of the veins. And they give an enormous amount of information about a person's health. In particular, they discovered by studying these images that they were getting much more information than diagnosticians were actually aware you could get. So by using the algorithms that I'm going to describe, this of course is still the teaser, you can look at it at the image of a patient and determine what their age is within some accuracy. Much more accurately, you can predict the gender of the patient. And this, we're told, is something that wasn't even known to be possible by the diagnosticians that had been looking at this for 100 years. And the parts that are highlighted here, this is the original image. The parts that are highlighted here are a form of what's known technically as attention. There's a mechanism that you can use to interpret the results of this. And the machine learning algorithm is just telling you what features it's using in order to make this determination. So to figure out the age, it's using lots of different things. Gender seems much more concentrated right around the optic nerve. That's where the optic disc is, where the optic nerve comes into the back of the retina. So it's not just age and gender. There are a whole bunch of things. Smoking. This is hemoglobin that tracks sugar over the past few years, BMI, body mass index. We know systolic, diastolic, blood pressure. And you get, when you're assessing patients, you don't usually get complete information on all of this. It's very inaccurate. And so by being able to use this image and reverse engineer all of these features that aren't otherwise available, this group, jointly between Google, Verily, and Stanford, published in Nature just this year, were able to make very accurate predictions of a person's risk of heart attack, or in some cases, a stroke. So this kind of diagnostics, of course, once you know what the features are, you could train somebody to look at the same thing and make the determinations. But at that point, why bother if the machine is already doing it better and more reliably? So we will be at the stage where a doctor will look in your eye, it'll be connected remotely to some machine learning software, and the doctor will tell you, I'm sorry, but you only have 5 years to live. Which, sounds bad, but it's better than, say, your self-driving car predicting that you have only 15 seconds to live. Okay. So what's the difference? What's going on here? This is I'm trying to just have some general overview slides so that the basic ideas come through before we get lost in the details. Traditionally, in programming computers, the methodology is you start with some data, you write some program to analyze the data, you feed the data and the program into a computer, and the computer produces some output. This is the way I learned how to write programs, sometime in middle school or high school in the late 60s. The new methodology is the data is some, say, fMRI scan of the brain. The task is to determine the probability of Alzheimer's. This is not possible, unlike the task I just described with the eye. But In this case, we don't know how to write the program. We don't know what to look at in one of these functional MRI scans that tells you how the brain is actually operating under certain tasks. What we do know how to do is collect what's known as training data. So we collect a bunch of these fMRI scans, and we have those patients who went on to develop Alzheimer's disease, those who did not. That's what we call the output. The training data is labeled according to the longitudinal outcome of the patient. And we put that training data and the output into a computer, and the computer writes the program. And that program is, as I'll describe, known as a neural network. It's the basis of deep learning. And the computer then writes this program that does the analysis. And the program then takes some test data based on what it learned in perhaps some inscrutable way from the training data and labels that we gave it. It feeds that program that it created, the neural network, the test data into a computer, and that gives an output, which is the prediction. So we didn't know how to write a program. Maybe we could have learned to write one by analyzing the innards of the program that it wrote, but in many cases, we're perfectly happy just to write that program. Although if we were doing fundamental science and wanted to figure out how to affect outcomes, then we could easily see this as being a tool to help us in the fundamental science, and the getting the output, the prediction for any patient wasn't the end of the story. Now, I wanted one other just general overview side, which I've, again, encountered when listening to someone far more expert than me giving a colloquium about this, to see why, it's not surprising in some sense that all of this is happening now. And, it was basically predicted about 20 years ago just by extrapolating where various organisms and hardware fell on a particular two-dimensional plot. What I'm showing here, it was made by a computer scientist named Hans Moravec at CMU in 1998. And on the horizontal, in a logarithmic plot, so each one of these bars is a factor of 10, that means it's increasing a lot, we've got megabytes, so it's some measure of storage capacity. On the vertical, I've got MIPS, which means millions of instructions per second, and for this, it's just representing sort of the bandwidth, the computational power. So you've got the computational power here and the storage here. And so you see Library of Congress has lots of storage, very little computation. Optical fiber and video channels are just transmitting information. They have lots of bandwidth, but they don't tend to store things. And then along this trajectory over here, you see things like bacterial spiders, home computer from 1996. Intriguingly, 1997 is a date we'll come back to. That was the year that IBM's Deep Blue chess machine beat Garry Kasparov in the World Chess Championship, the first time a computer had beaten the chess champion. And intriguingly, the computational power and bandwidth of that machine was roughly that of a mouse. And so compared to animals and what animals can do, when you focus on a specific task, you are getting an uncommon amount, an uncommonly effective program for that particular task. And then the point of this is, if you keep going up, computers are now in this human, whale, elephant stage. But the real punchline here is that we can estimate that by 2030, in a little over a decade from now, for just $1,000, you're going to have computational resources that match the human brain and storage capacity just on some small mobile device. And that's just one device. That's not considering the cloud. So if you consider the cloud and your millions of devices, that's where the Skynet in my title came from. So it's not surprising that we've, given that we've reached this threshold, that we have all of these new and wonderful applications. Now I have to check the time. Okay. And so I want to give a quick overview of how this works. And you might think, given how extraordinary the results are, it would be impossible for me to explain this. But even with experts here in the audience, I'm going to give an overview of this, which I claim is both elementary and captures all of the essential aspects of it. So to start with, I want to back up to what we teach as one of the first aspects of a machine learning course, which is something that goes by the intimidating name of least regression. But let me just explain to you what's here. These blue things are points, data points. Maybe they're represent the price of cars and the manufacturer suggested retail price of cars, and perhaps their gas mileage or the power in their engine. And we're not, we have this cloud of points. They don't fall exactly on a straight line. But what we're interested in is the overall trend. In particular, if we look at a graph like this, I've drawn a red line, which is a good linear fit to these points. And what it's telling us is if we were looking at something, whatever is being plotted here at 55, it's likely to be in this range. It's likely to be in whatever this 11 or 12 range is. It's almost impossible based on the data we have to be down here. Similarly, something down here is not going to be up here. So what we mean by regression line is just some rough fit. It's not going to be exact, but it's telling us the general overall trend of the data. The other basic problem, and so that's regression to infer roughly what a number would be in data from over here if we had an X value that wasn't already in our data, and to make a principled guess as to what it's most likely to be. The other one is a classification task, and here I've shown I'm using, again, in this two-dimensional plot, and we'll have to, this is the most any of us can really visualize easily. But the idea is that if we had some new unknown point here, all of these blue ones are one class. Maybe it's spam email, and maybe this is non-spam, or vice versa. Maybe these are sports articles. Maybe these are politics articles. If some new unknown point, whatever we were using to place it on this two-dimensional graph, came out of here, we would overwhelmingly say it's in the same category as this one, and vice versa for over here. And there was supposed to be a line that came down there. Okay. So I guess I animated the line. So I left this in. The next few slides I borrowed from a colleague. And I left this one in because I was just wondering if, since we're already at 8,000 feet, do we have to change that to an overview from 18,000 feet? OK, so this is the slide I thought I had. I didn't organize them well enough. For this particular classification task, and this really is, I use, well, my colleague Killian used spam email and non-spam email. And the answer to this case was given by the primordial neural network, the one that effectively underlies many of the things that we're now doing and anticipates them, by Frank Rosenblatt, who coincidentally happened to be a Cornell undergraduate and did some of this work while he was still affiliated with Cornell. And it was called the Perceptron. And the answer, which is what I was expecting when I clicked before, is the classification task, just as in the case of the regression, solved by a line. Here it's solved by a line again, but it means something else. It means things on this side of the line are non-spam email. Things on this side of the line are spam email, determined by the placement of the points, or what words they contain, whether they contain red blinking fonts, and are exhorting you to buy things, and all the rest. this classifier in a way that I'm going to describe. I haven't said anything about what this thing is yet, but we're going to get used to, over the next 5 or 10 minutes, these diagrams which represent this network. I'm leaving it in here only to indicate that this perceptron is the first example. Now, there's an important point here, which is, of course, that the dependencies are not always linear. If we look at a bunch of points like this, we could try to fit it with a straight line, but it's high here, low there, and it would be much more natural to fit it with some line like this. So although dependencies are not always linear, there's a trick question here. I'm curious if anybody knows. In what state, by law, are they linear? So there is a state where it says rates of sea level rise may be extrapolated linearly to estimate future rates of rise, but shall not include scenarios of accelerated rates of sea level rise. So some state has determined, for political reasons, that you're not allowed to use nonlinear fits to how fast your shoreline is accelerating. Where do you have to be careful about going to the bathroom? You got it. OK. So this kind of stuff really happens. But in general, the point I was trying to illustrate is, and happily we're not constrained by North Carolina law here, we could have points that look like this. And the solution to this, Rosenblatt's original 1958 perceptron worked when you had a straight line, but you add, and I'll explain what this is in a moment, but instead of that simple version we had before where there was one set of inputs and directly an output, now you have this mysterious hidden layer, which is not, which doesn't receive inputs. It's not directly giving you an output, but its units are used together to produce some output. OK. So the question I'm now going to pose is, in both of these cases, we had some data, and we were trying to fit a function, in the case of regression, to predict how fast things were going. In the case of classification, just to predict where they fit according to some class. The class could be, the data could be, instead of the two-dimensional data, the data could be the values of the pixels of 1,000 by 1,000 image, and the classes could be what animal does it contain, or 1,000 different classes according to what it contains. So the general task that we have is to take all of those pixels in our image and find some possibly incredibly complicated function, but according to the values of all those images, tell us, does that image have a dog or a cat? And so in principle, at least, we could imagine there is some complicated function, extraordinarily complex, but which could compute on those pixels of an image and determine its class, or in the case of those retinal images, somehow magically figure out gender and risk of heart disease. So in order to do this, I have to finally get to describing what the nature of those nodes I've been describing, depicting are. So we call this thing a neuron. We call it a neuron because the original idea behind these neural nets were modeled after things that the brain is doing. So in the brain, you have neurons that fire, they don't fire. They feed into other neurons, and how much they excite some other neuron depends on the strength of the connection between them. There's an axon that hits a dendrite, and some acetylcholine goes across that, and those things can be modified over time. That's how we create memories, and our brain also uses these things to compute. And so that was the original motivation we're not currently using them in that sense. I want to emphasize that there remain a bunch of parallels, but these things have evolved in the 50 years since Rosenblatt and his perceptrons to be much more of an engineering exercise. Let's just construct the thing that performs as best as possible for that task, and let's not worry about re-engineering how people can do it, because maybe we can come up with something better. So the basic unit I'm going to describe is one that was pretty much become standardized much later on in this history, only in, say, the past 5 to 10 years. It's called ReLU, standing for rectified linear unit, which is still intimidating terminology, but I will tell you it's the very simple thing. We've got an x running along the axis, and the function it describes is here's x equals 0. If x is less than 0, the thing just tells you 0. If x is greater than 0, it just returns x. So very simple function. The line y equals x would be here, and we've just sent all of negative x to 0. And that basic unit, as I've described it, I can very easily show you how it could be used to approximate almost any function. And so now I get to tell you what these lines mean that I already had on some of these graphs. This is a neural network, and I want to describe a one-dimensional function of x. And I'm going to have one input neuron. These 3 neurons are my quote-unquote hidden layer, and here's the output. And I want to use it to approximate some function. The way it works is on this line, there's something known as a weight and a bias. And it just does your favorite equation from, for some of you like me, junior high school, otherwise middle school, which is the formula for a straight line. Y equals ax plus b, where a is the slope, b is the y-intercept. So W1 is a weight associated with this connection. B is just known as some bias you added on. And you feed this thing into this node, and then this node is a rectified linear unit. So the output of this node is just when W1x plus b is greater than 0, it just outputs some line with slope W1. This thing is equal to 0 when x is equal to minus b1 over w1. And so that tells us for x larger than some value, I'm assuming that the w here is positive. It looks like this. And I can do that, same description, different weight, different bias. And in this case, I'm assuming that the weight is negative, so it has a negative slope. So this means when x is small, the thing is positive, and then when x gets large enough, this negative weight outweighs this bias, which I'm assuming to be positive. And so this one turns off at some critical threshold. Again, the bias over the weight. And then it's the same story for this one. On this one, I've assumed, again, a positive weight and a slope that is even larger than this one. So W3 is greater than W1, and again, this one turns on. Now, the final trick here is that these 3 hidden neurons feed into our output layer. This is the one that's going to generate the function we want to approximate. And you get more weights. So whatever this thing is gets added onto this one with weight multiply this thing by v1, multiply this one by v2, multiply this one by v3, add them all together, and the result in this case I've depicted like this. So what's going on here? Well, in this part over here, this one's turned off. The only one that's turned on is this one, and so it generates something with that slope. At this value of x, remember is moving along the horizontal, this one turns on, so that slope is now reduced. Well, that slope is now reversed because this one is going up faster than that one's going down. At this point, this one turns off, so this one starts going up at the higher slope. This is now the only one that's turned on. And then finally, at this last threshold, this one turns on, Remember, this one has a negative weight, and so that takes the slope down. So that's basically it. I want to leave this diagram up for a moment or two, because with basically no approximation, this is what's underlying every one of these applications that I mentioned in the first few slides. The ability to approximate a function by just piecing together little pieces with different slopes. It's easy to see if I had an arbitrary function here and I had enough neurons, I could just thread in one over here. It's what's known mathematically as a piecewise linear approximation to a function. To any desired accuracy, I can just add enough of these neurons, turn them on at the right point, give them the right slopes, have all the slopes add up, and I could have an arbitrary function. And so since this is so important, I have a demo, and every time I give a demo, the question I have to ask myself is, do I feel lucky? This one was particularly problematic because when I was trying to do it, I ran into one of these annoying Python things, which is they quote unquote updated the widgets so that it broke this demo on my own computer, and it would have taken me hours to back out of the latest version. So I found another computer at work that didn't have this problem. So this is a demo I use in my class, so I will have to fix it eventually. And it permits me just to interactively choose points. And I want to choose my points in some interesting way. And in real time, it's just calculating a linear slope. But I'm going to give it something that's much more difficult to calculate than a linear slope. And then finally, I don't know, something like this. Okay, so now what this thing does, and with a remarkably small amount of code, I'll show you the code afterwards, I can just feed in the number of neurons. So if I only put in 2 neurons, that's this. I lost my. I'm showing the 2 neurons over here. There's 1 input, 1 output. There's not a whole lot it can do. It can just feed in one of these slopes and it gets some linear approximation. If I put in 4, it depends. Sometimes it'll get lucky, sometimes it won't. And that's doing a little better, but still, and you can see this thing running in real time and it converges. But not surprisingly, usually at around 8, it starts, it's just, and it's actually, those colors are telling you, I guess I don't have, the outer circle is whether it's turning on or turning off, and then the color going from red to blue is whether it's a negative or a positive slope for each one of these 8 neurons. And it's just telling you what it's doing. And as you increase the number of neurons, this is just to indicate, there's 16, and it gets better and better. And I guess I'll just skip directly to 64. And at 64, basically, you'll get something. It takes a little while to converge. But now you have so many degrees of freedom. Basically, this thing is going to, there's some way of running this longer, if I remember. Yeah, oops, no, I just did the same thing again. I guess I had to, I just forgot. Haven't done this for a while, but I mean, you get, it's already doing much better this time with 64. It's basically going through every point, and I think if I just put this thing, if I put it in with no number, then it just continues. And eventually, this number down here, which is just measuring the sum squareds of the deviations from all these points, will go down to 0. So this is meant to illustrate in a way where we can really visualize how these neural networks are approximating functions, and the extent to which I assert that this is with actually very few approximations what's going on in the higher dimensional sense is that instead of just one feature, we have these million features from 1,000 by 1,000 photograph. And we just have a function like this on each of them. And of course, the function is not just, if it were just one y value, it could tell you, is this a cat or is this not a cat? But that function might have 1,000 values telling you the likelihood of 1,000 different objects that might be in there. But all of this generalizes to higher dimensions in the sense that instead of just some line in there, it's a piece of a surface, a piece of a flat surface that can be 2-dimensional, 3-dimensional, 5-dimensional. It's just known as a simplex, but the basic idea is exactly the same. You've got some surface that you can't even visualize in some higher dimension, but you're just taking little pieces of flat stuff and feeding them in. So while I'm off my PowerPoint, let me just do one other demo, emboldened by a rare moment of success here. So here's a demo that, actually, I should give more credit. I adapted this from a Stanford course. The TA there was a fellow by the name of Karpathy, who was a grad student at Stanford at the time. And he now has the wonderful job of being director of AI at Tesla. So the idea here is just to give you, I mentioned we were just doing a regression task. Now the problem is to take something like this that looks sort of difficult and classify the different points. They're intentionally put in these spiral patterns, so it's difficult. And I can run something that tries to do this in real time on my laptop using a linear classifier. So a linear classifier would just be a single network. My two inputs are these 2-dimensional coordinates. My 4 outputs are which of the 4 colors I think it's going to be. And when I run that, this is actually now running in real time on a simple linear network. And you see, not surprisingly, it doesn't do that well because there's this entire problem with these spirals is chosen to be difficult to fit if you're just working with straight lines. After 500 iterations, it only correctly gets about 30% of them, which is better than random 25%, but you wouldn't bet your life on this. Instead, again, the same thing. We've got these 2 inputs. We still have 4 outputs, but now we throw them through these 8 other units, just like we had 3 over here. I think actually in the online thing here, I picture 8, but it actually, I'll actually be using 100. That's this number right here. With this nonlinearity, the analog of the rectified linear unit. And so now I run this thing, and it starts out looking bad and actually has me quite worried, but fortunately I've seen this before. And then as it iterates, it gets better and better and better, just with that single nonlinearity. We're in Colorado, it's okay. And I don't actually know how long this is going to iterate, but I think it's possible I let it iterate until it, I'd have to look back at the code, but it just goes to 10,000. Okay, so now it's again, in exactly the same way, what all of these 100 hidden units do are give us the opportunity of piecing together these little pieces of surface, and it can use those to figure out how to put all of these points together. And just as I showed in the case of the linear regression, if we have a new unknown point over here, it's likely to be one of these light green ones. If we have a new unknown point here, it's likely to be a blue one, and so on. It's using, and of course it gets, it doesn't do a great job with respect to our intuition over here. We would probably guess it goes more like this, but it does the best it can with the data it has. So now, I want to do one thing. I'll show you. I need actually to add a slide that I realized I wanted. So my preparation here was a little, I just remember thinking, how could I not have said anything about back propagation? Okay. All right, so we'll get that in a second. Now you know how much effort goes into these slides. Okay, so this is the, for that demo that I gave, the first one that showed using hidden units where I went 2, 4, 8, 16. This is the entirety of the code. This is it. This is how simple these things are. Conceptually, they're very simple. The question is, what did I use to do the fit? Or, more importantly, in the example I just gave of that 4-color classifier, I wasn't in trouble before, but I am now, to figure out what the values of these weights and biases were. And so for that, I wanted to give an intuitive demo of what's known as back propagation. And I warned them that I was going to take my chances and get up on stage here, just so you can see it. They were worried, but I promised them there would be no slides. So the best I could come up with as we were driving here, thinking about this is, suppose you have some goal, and you've got a bunch of parameters that you want to adjust in order to achieve that goal. And so the example I came up with is, suppose I'm learning how to shoot a basketball. So I take my basketball, the rim's over there, and you shoot, and you hit the back of the rim. And so you know what your target was, and you want to adjust your parameters so you get closer. So I hit the back of the rim, and so I won't push it quite as hard. This time I hit the front of the rim, but now I go backwards. I see by how much I missed my target, what would I have to do to get closer to that target? And so I don't push it quite as hard. Well, I already tried not pushing it as hard, so now I give it a slightly higher arc and a little more push, and then it hits the front rim and dribbles in, and so that's sort of successful. But then I figure out from that, I sort of back propagate from where it got to what I would need to do to get all of those cats classified as cats and all those dogs classified as dogs. And I give it just a little more and a little more arc, and that time it was nothing but net. And you can't see it, but I'm behind the 3-point line. So, so that's basically all that's happening. All right. Okay, so I'm going to move a little faster. I have a gigantic history here, and so this is actually good. It's a good way of jumping right into what's going on with these much deeper networks that people are using now. I can describe it. There's a much more complicated architecture. I've just been describing simple architecture. I asserted that you could do anything you wanted with a single layer, but it turns out, for computational reasons that I'll get to in a moment, it's actually more efficient, instead of using one really wide single layer, to use a lot of much narrower layers. And these layers do things which are much more similar to what happens in the layered structure of the brain, where we know the visual cortex is the first few layers of neurons after the retina are understanding, say, moving lines. This was the classic work of Hubel and Wiesel in the 1960s. And then later layers, the idea here is this layer would see lines, and then this layer would see curves and circles, and then this layer over here would start assembling them into things that look like cars. And then you have a very complicated function. As I said, it's got to be massively complicated to take not just a single input, but some large number of inputs, and then in some possibly inscrutable way, and the final, it tells you whether it's a car or not. And the second slide, which just is useful to recall what the basic, there were a variety of machine learning techniques that predated all of the modern fancy deep models. You would have to figure out on your own what the features were. So you would have to, hand determine, hand code, okay, if this thing has a wheel and it's a circle and it's located there, of course it could occur anywhere in the image, so that was, you'd have to look for it anywhere, and handcraft some large number of features that would indicate car to you. Whereas what's going on in these deep models is it's doing all the heavy lifting. You didn't have to figure out anything. It figured out these low-level features. It's got these intermediate-level features, and then these high-level features that ultimately produce something that can reliably distinguish all of these different objects. And this is what, actually, I guess, 1959, this is what I was just anticipating when I mentioned these classic experiments of having an anesthetized cat look at images on a screen and probing what was going on in these various pieces of visual cortex. And as I emphasized, there are this layered hierarchical approach, which is so powerful, not surprising that something similar developed in mammalian brains. It's not doing exactly the same thing, but it's very analogous. So I'm going to go, the last thing I promised was an overall history of, the prehistory of the modern stuff. I'm happy, I wanted to convey that essential point with the demos, and I'm going to just skip through this very quickly so I can get to my final slides, but just mention a few things. The neuron that's being used is called the McCulloch-Pitts neuron. Goes back to 1943, and it's exactly what we were showing. It was invented back then as a model for dendrites. You put in activations with weights, it sums them up, and then if it's greater than 0, it lets it through. If it's if it outputs a 1, if it's less than 0, it outputs less than 0, it outputs a 0. You needed some notion of learning, that is, these weights themselves, activate in the same way probably our neurons that activate. When we think about our grandmother, there's some neural pathway that gets set up, and every time we think of her, it gets reinforced, and they actually see these things when they stick electrodes into people's brains during brain surgery. Rosenblatt, I mentioned, this was this perceptron where you have that function I mentioned. This was realized not on a computer, but mechanically. He had some mechanical device that implemented this perceptron and used it to classify 20 by 20 shapes. And just to show that hyperbole isn't restricted to the modern world, looking back at the 1958 New York Times, Dr. Rosenblatt, Cornell, later perceptrons will be able to recognize people, call out their names, instantly translate speech in one language to another, it was predicted. He said, in principle, it would be possible to build brains that could reproduce themselves on an assembly line and which could be conscious of their existence. So that's something of a stretch, given that this particular demonstration was fed 2 cards, and the task was to learn whether a particular square was on the left or the right. So something of a stretch, but he got to general artificial intelligence from this. I'll skip over this. There was a period, this field has had what are known as winters and summers, and so I don't have time to do justice to this. I'll just tell you that there was a long period from the late 70s, 60s through the 70s, and the New York Times, ever eager, exclaimed that after 2 decades of research, they have yet to teach machines the seemingly simple act of being able to recognize everyday objects and to distinguish one from another. So everybody was dumping on the field. And there were nonetheless a number of developments, and I'm sorry I don't have time to talk about the 1980s, but that's when many physicists got involved. There was a spin system known as a spin glass, whose finding ground states of which was very similar to finding the solution to these relaxation problems I demonstrated for you. And when I got into the field, I was treated to a wonderful comment by a physicist, Miguel Virasoro, who said that physicists, having failed to use their brains to understand spin glasses, are now using spin glasses to understand their brains. So you've seen all this. This is a development in the mid-'80s known as an autoencoder. You feed inputs into a smaller hidden layer. You treat it so it produces outputs that are as close as possible to the input, and that gives you a compressed version, very useful, of the same inputs. Late 1980s, Yann LeCun invented these so-called convolutional neural networks, which have been used so much, but many of us don't necessarily realize that they were already well in place in the late 90s for reading checks at banks. And then I have to say something about backgammon, because it underlies so much about what's been going on with chess and Go. And it's, again, a wonderful example. So backgammon is this game with black and red pieces, say, and they move in different directions. And a researcher at IBM by the name of Gerald Tesoro created something called TDGammon in 1992. And it used the same methodology, only it was more indirect. It used something known as reinforcement learning, where your goal is, your reward is delayed many steps. You're looking at a position of the backgammon game, and you have to go many steps in the future before you learn whether it was a winning move or not. And the power that Tesoro, who himself wasn't a terribly good backgammon player, I'm told, he just had this thing play against itself. And that turned out to be the most powerful way, the one that's been used to such great effect for Go and chess and shogi and Atari games and all the rest. With playing itself 300,000 times, that took a month of CPU. Now it would be, presumably a few minutes. He got a competent player. He moved up to 800,000 times, and he was comparable to the world players. And with 1.5 million self-play games, he was then evenly matched against the world champion, and just involved playing against yourself, something that a computer is perfectly happy to do. And I wanted to emphasize it's not, it not only opened up new vistas and strategies for human players. Back then, in the 1990s, it already inspired numerous follow-ups, elevator dispatch, various optimization problems, financials, trading, portfolio management, and the rest, and military applications. That's something, where the funding, Go especially, was originally a military-inspired game where you try to surround the other one's pieces. So you can imagine if you're, directing military, you want the best AI. These games are actually a fantastic way of experimenting. You play against yourself with the best strategies, and you can always win. Okay, move quickly. Just to indicate who are the major players that brought us out of that phase where the New York Times was dissing them. Geoffrey Hinton, receiving funding from the Canadian Institute for Advanced Research, was a wonderful thing. I should mention in this period, and I've heard from the major players in this, that they were very upset because their articles on neural networks were being rejected from their own conferences. And so they got together for dinner in 2006. I'm told this is a real story. True story, and said, look, everybody hates neural networks. We have to rebrand. And so over some wine, they came up with, well, what about if instead of neural networks, we call it deep learning? Because, you'd have to be in favor of, I don't know, shallow forgetting to come out against it. So that succeeded. At the time, the state of the art in recognizing digits was just decreasing incrementally. But Hinton, using his money, had discovered with GPUs, these graphical processing units, thanks to people like my children who spend all their time playing games on their computer, they put a lot of work into creating this hardware for graphical processing units. And that turned out to be optimized for exactly these kinds of calculations I just showed you, where instead of just adding up 8 things, you could add up thousands or millions of them incredibly efficiently. And the result of this was by decreasing the training time, you could experiment. You could experiment with how to initialize the thing. You can experiment with what kind of nonlinearities. And in this 2011, 2012, suddenly the performance on these image recognition tasks, I'm just flashing the people, I'll show the overall thing. This is the task, 1.2 million training images, 1,000 categories. And I just remember how thunderstruck people were. I was going to seminars in this at the time where they achieved an error rate which was dramatically lower. After these tiny incremental changes, suddenly error rates were dropping by around 10%. And here's a graph of it in the pre-deep learning stage. So when I went to the same conference now called NeurIPS in 2015, multiple speakers got up. It used to be that you could not get a paper into this conference if it was about neural nets. Now you can't get a paper into this conference if it's not about deep learning. And you can see in this image recognition task, they've now gotten it to the superhuman performance level after this dramatic jump. And that was coupled, and of course, now the New York Times, a different reporter comes back and breathlessly describes the new software, which researchers at Google and Stanford University, I guess appropriately, taught itself to identify entire scenes, including young men playing Frisbee. Which is presumably regular activities there. So the why us, why now question, I've more or less tried to explain. Some of it is just the big data era. We have much more storage. Some of it is the GPU that I just mentioned. Here's a picture of a GPU. And which reduce the training time, you could find better heuristics, initialization, nonlinearity. Some of it is just all this wonderful software that people have produced, and you don't have to do the kind of thing that I did. You just, from TensorFlow, import star, and you're ready to go. So here are some of the things that I won't describe. I want to, I'll run a minute or two over. Just point out these things that happened from 2013 to 2017, including the original AlphaGo program, the Texas Hold'em, the later AlphaGo program beating the world #1. I want to pause for a moment on some of these events from 2017. Specifically, the development here was an AlphaGo Zero, which then generalized to AlphaZero, which is you no longer gave it any human input at all. You could take a chess-playing program. It's what they called a tabula rasa, not remembering. I remember my y = ax + b better than my Latin from junior high school, but it means scratch tablet and means clean slate. So you don't use any prior human chess games. You just throw this thing and it plays against itself for a few hours and has played more games than have been played in the entirety of human history. And Gary Kasparov, in a editorial in Nature just last month, said that without being biased by the human knowledge, this therefore comes much closer to the truth. And that may well be. In this case, the style of play it came up with was this highly open and attacking style of play, which coincidentally happened to be Kasparov's style. Medical image analysis is I mentioned some of that. I have to emphasize now the entire MRI processing chain is segmentation, disease prediction goes through this. AlphaGo Zero, and it's just all pervasive. Google search, image search, driverless cars, voice recognition, everywhere you go. Major companies are hiring like crazy. So I'm now at exactly -2 minutes, but, and this was nominally my final slide, so I haven't done disastrously awful. I wanted to say something about how these feed into science problems. Some of them are like Go, like protein folding. There are well-known rules, well-described goal, and so you could easily imagine, and it's true, that similar algorithms might be implied to tasks like this in quantum chemistry, material designs, and robotics. So this game playing has military applications, also has a variety of scientific applications. And because there are some very pretty images, I wanted to describe one other major development. It was on that timeline as 2014. And it's wonderfully easy to describe. It's known as a generative adversarial network. And you just turn everything into the kind of games that we've been playing, like Atari or chess or Go. The idea here is you've got one neural network that generates images, another neural network that discriminates fake images from real images, and you have them play each other. And so the one that discriminates the real images from the fake images gets better and better, but the generator gets better and better at generating things that look much closer to the real image. And then finally, the discriminator achieves superhuman performance. It can discriminate real images from these artificially generated images, and therefore, humans can no longer detect them. And this has been used to great effect, but as I'll mention, there are some. So this was trained on a database. These are all artificially generated images. They're not real people. As is probably evident, there were multiple pictures of me in this training set. No, this was probably, I think, Hollywood celebrities. And also works just for arbitrary natural images. You set this thing up, it can generate images, and they're indistinguishable from real. None of these objects has ever existed, and once you can see things like that, you have to question your grip on reality. Oh, I almost forgot this one. Creativity. This sold at Christie's in October. They were anticipating $7,000. It sold for $432,000. And the signature here is probably too small for most of you to read, but I've enlarged it. And the experts in the audience will recognize this is the cost function that was being optimized in order to create to train this particular neural network. So, there's some intimation of creativity. Could we have, neural networks that produce articles? There's a big problem there, because if you can produce such realistic things, you could also produce what are known as deep fakes. So, a pornographic image with, the face of a politician, or an absolutely photorealistic picture of the current president with a porn star. No, I guess that wouldn't really have any effect. But there are a variety of software that uses fingerprints for identity, and there are already these GAN-type models that are being used to produce master fingerprints that can deceive them. And also there are programs that automatically are trained to generate messages on Twitter that people are likely to click on. And so, a vast significant potential for exacerbating a lot of the societal problems we're now seeing. Okay, so the last we really got to finish. So maybe I'll just get this down to a few sentences. I was going to use this to just illustrate this is where I'm really on unstable footing and outside of my, my realm. The question is, what effect will all of this AI have on society? One thing we've already seen and actually probably has contributed to the demographic shifts and some of the weirdness many of us were not prepared for in the 2016 election is all of these job displacements. Economists always say, oh, well, technology is good. It replaces some jobs, but it creates new jobs, and they're even better. And that hasn't been happening this time around. This time around, it's taking away secure jobs and replacing them with lower paying jobs without benefits and all the rest. And this gig economy like Uber and Lyft. There are lots of ethical questions that I didn't expect to have time to discuss. If a self-driving car has an accident, who's at fault? Is it the programmer? Is it the manager who signed off on the program? Is it the company? Same thing for a military. Suppose some missile strike is launched and it's all an accident. There's AI used to assess crime risk, and this one is one where people have pointed out, there's this company Compass that provides something for judges to decide whether people should go to jail awaiting trial or be let out on bail, and point out that white people are, the software appears biased between white people and black people, that with the same features, somebody with one race will get more lenient treatment than the other systematically. And that's not actually the bias of the software. It's the bias of the data that's put into it. And this particular case, you can easily imagine, they just say, oh, well, this person lives in a neighborhood that has much more crime. But that neighborhood has more crime because there's more of one race than the other. And actually, it might not even have more crime. It might have more crime reported because there is a greater police presence in those areas. And so you just have to be careful about what you feed these things. And the last thing I was going to say is people talk about how it could be the end of science because you replace creative thought with these things that just find correlations. This was a slide that was used this morning at the conference we were at. And I just want to say I'm not terribly worried about that. The fear would be, as I said in the case of the retinal data, suppose somebody had the data, from my own field on quantum fluctuations, and there were these completely mysterious correlations that we could never figure out, but that systematically, could be used to predict the results of the 2020 election. And it would seem like an oracle to us, and we would try to probe it, but it might be that it was, too difficult to imagine. But I don't think that will happen. I think these things will just remain tools like computers, special functions, and all the rest until we get used to them. And then the final question I just wanted to touch on, and I'm not deliberately filibustering against the question period, but was, can computers be conscious? Could we imagine these things being general artificial intelligence? And with great risk, and this was the real reason for my thin ice, if you take a particular worldview, which is the materialistic worldview, which is, sort of as a physicist hard to avoid, that everything that goes on in our brain, involves physical states, neurons firing, connections between those neurons, it really is inescapable that we could eventually might take a unbelievably powerful computer, more powerful than anything that we, could imagine, but at least in principle, a big enough computer that could simulate all of the neurons in the brain and all of their activities and all of their connections would, be, even including quantum computers to take into account quantum effects, would be ultimately indistinguishable. In fact, we could imagine a generative adversarial network where a discriminator tried to tell the difference between this and a real brain. And in that sense, you might think, and I'm not comfortable saying this and I won't argue for it, but it's hard to escape the notion that computers could have something that's analogous to what we call consciousness just because it's just there in these electrical signals. So with that, I'll stop and apologize for having run over. I'm told they will kick us out at a quarter to the hour. Thank you. One or two questions? Yes.
So when you talk about theories of things, just to write that on that point, the way that things are computed now, there are the speakers before at the cafe were talking about a more biological standpoint and maybe not having, doing things more efficiently that aren't necessarily modeled after our brains. So in that theory, could we more easily then create some form of human that's obviously a lot more efficient than we are, smarter, faster, doing things differently? Why are we still trying to create us?
I think that's a very insightful question. And again, from my inexpert point of view, given that that's the way all of the rest of this has gone, that's the likely way, it will go for what's known as, general artificial intelligence, the ability to do anything we can. And then, yes, absolutely, I was exaggerating. I certainly don't think it's necessary to do a full-scale simulation of everything that goes on in the brain. And then the question we're asking is, how small would it have to be to capture all of the essential aspects? And, I would guess it would be much smaller. And then, we have to ask whether that will come under, government regulation because, who knows? These things always do.